The chain rule is a way to differentiate composed functions. It says that the derivative of the function f composed with g at x is the derivative of f at g of x times derivative of g at x. In this video I discuss the chain rule, and I start by reminding what composed functions are. If f and g are two functions, the composed function f circle g is defined by setting its value at x to be the value of f at g of x. Observe that f circle g, f composed with g, can be defined by this formula whenever the range of the function g is contained in the domain of definition of the function f. Let us take a look at an example. Consider the function w equals x squared plus 1. It takes a number x on the x-axis to the number x squared plus 1 on the w-axis. We may further proceed with the function sine of w to the y-axis. So now we have two functions, the function indicated by the blue arrow w equals x squared plus 1 and the function indicated by the red arrow y equals sine of w. The composed function is y equals sine of x squared plus 1, and it is composed of the two functions w equals g of x, which is x squared plus 1, and f at w equals sine of w. Recall that the derivative of a function f at a number x0, f prime at x0, is the limit of the difference quotient, limit as h goes to 0, of f at x0 plus h minus f at x0, and that difference divided by h. For the existence of the derivative, we assume that this limit exists and is finite. We do not allow infinite derivatives. Now, as already noted, if g is a function from x-axis to w-axis and f a function from w-axis to y-axis, then we may form the composed function f composed with g, assuming that f is defined in the range of g. So in what follows, we assume that f and g are such that the composed function is always defined. Then we have an important result which says that if g has a derivative at x equals x0 and fw has a derivative at w equals g of x0, then the composed function has a derivative at x equals x0. This is a deep result, and in the end of this presentation we will prove this result using differentiability. The chain rule can be used to compute the derivative of a composed function. According to the chain rule, the derivative of f composed with g at x can be computed as the derivative of f evaluated at g of x times the derivative of g. This chain rule can also be written as df gx dx equals f prime at gx times g prime at x. This may be the more convenient way of remembering it. Let us take an example of the use of the chain rule. And in this example, we consider the composed function that we have already seen in another example. So our task is to find the derivative of the composed function sine of x squared plus 1. We call this function h. And this is a composition of two functions, f and g, where fw is sine of w and g of x is x squared plus 1. The derivative of the outer function f is cosine, and the derivative of the inner function x squared plus 1 is thus 2 times x. So using this, the derivative of the composed function h prime is derivative of f evaluated at g of x, that is cosine evaluated at g of x, so cosine at x squared plus 1 times g prime at x, which is 2 times x. So the answer is that the derivative of this function h is 2x cosine x squared plus 1. The following simple argument is often presented as a justification for the chain rule. The derivative of the composed function f composed with g at x is the limit of the difference quotient for the same function, that is, the limit as h goes to 0 of the quantity f evaluated at g x plus h minus f at g of x, and that difference divided by h. Now we multiply and divide by the quantity g x plus h minus g of x, and we get that the difference quotient becomes the product of these two fractions, f at g x plus h minus f at g of x, and that divided by g x plus h minus g of x, and that multiplied by g x plus h minus g of x, and that divided by h. Now we have this presentation for the derivative, and the limit of a product is product of limits. So we have that derivative of f g of x dx is limit as h goes to 0 of the quantity f at g x plus h minus f at gx, and that divided by g x plus h minus gx, and that multiplied by the limit as h goes to 0 of g x plus h minus g of x, and that divided by h. Now, the first limit is the derivative of the function f evaluated at g of x by the definition of the derivative, and the second limit is the derivative of g at x. Therefore, we conclude that the derivative of the composed function f composed with g at x is the derivative of f at g of x times derivative of g at x. This argument has one problem, namely if g x plus h minus g of x takes value 0 somewhere, we cannot multiply and divide by it. So this is correct only if g x plus h minus g of x is different from 0 for all h different from 0. This is a mild restriction. In many cases, this assumption is true, and this argument then can be used to justify the chain rule. The chain rule may be used repeatedly to differentiate complicated functions. For example, the function w, defined as wx equals e to the sine at cosine of x, is a function composed out of three functions. The outermost function is the exponential function. Then we have sine, and then finally cosine. The derivative of the exponential function is the exponential function itself. Therefore, when we apply the chain rule once, we get that the derivative of this function w is e to the sine cosine of x times derivative of sine cosine of x dx. The derivative of sine is cosine. Therefore, by using the chain rule, again here, we get that the derivative of this function w is e to the sine cosine of x times cosine of x times the derivative of cosine. The derivative of cosine is negative sine, therefore we get that the derivative of the function w is minus e to the sine cosine of x times cosine at cosine of x times sine of x. To summarize, the chain rule says that the derivative of the composed function f composed with g at x is the derivative of f at g of x times the derivative of g at x. Rules to differentiate functions fall into two categories. First, there are general rules. The first general rule says that derivative of a constant is 0. The second one says that the derivative of the identity function x is 1. The third is a constant multiple rule that says that the derivative of a constant times a function is that constant times the derivative of the original function. Fourth rule says that the derivative of a sum of functions is sum of derivatives. Fifth rule says that the derivative of a product is the derivative of the first factor times the second factor plus the derivative of the second factor times the first factor. The quotient rule says that the derivative of a quotient is denominator times the derivative of the numerator minus numerator times the derivative of the denominator, and that difference divided by the square of the original denominator. The chain rule, the topic of this video, says that the derivative of the composed function f composed with g at x is f prime evaluated at g of x times g prime at x. Of these general rules, rule number 3 and rule number 6 are not absolutely necessary, because rule number 3 follows from the rule number 1 and rule number 5 immediately, and the rule number 6 follows from rule number 5 also. Then there are special function rules. We have already remarked that the derivative of x to any power r is r times x to the power r minus 1. The derivative of sine is cosine. The derivative of cosine is negative of sine. The derivative of the exponential function is the exponential function itself, and the derivative of the function tangent is 1 divided by cosine squared. These rules one must remember by heart. A moment ago we presented a justification for the chain rule using the definition of the derivative as the limit of the difference quotient. That justification is not quite general. There are situations where it cannot be applied. A rigorous proof of the chain rule can be based on differentiability. Let me start by recalling the notations related to differentiability. For a function y equals f of x, we denote by delta of x the change of the variable x, that is delta of x equals x minus x0. The change in the function values, that is delta of y, is y minus y0, f at x minus f at x0, and with these notations we defined the differentiability by saying that a function f is differentiable at x equals x0 if there is a number a, the differential of f at x0, and a function epsilon, such that delta of y is of the form a times delta of x plus delta of x times epsilon delta of x, and epsilon delta of x goes to 0 as delta of x goes to 0. So this is the definition of differentiability. Recall that we have previously seen that a function f is differentiable at x equals x0 if and only if that function has a derivative at x equals x0. If this is the case, then the differential of the function at x equals x0 is the derivative of the function at that point. Therefore, being differentiable is the same thing as having a derivative, and the differential is the derivative. We use this fact to justify or to prove the chain rule for composed functions. So we assume that a function g is differentiable at x0, that is, has derivative at x0, and f has a derivative at v0, which is g at x0. Then, by the definition of differentiability, we have that fv minus f at v0 is f prime at v0 times delta of v plus delta of v times epsilon f delta of v. Likewise, for g we have g of x minus g of x0 equals g prime at x0 times delta of x plus delta of x times epsilon g delta of x. These functions epsilon f and epsilon g appearing here have the property that their limit is 0 as their argument approaches 0. These are the functions that we had in the definition of differentiability for general function. This function epsilon will depend, of course, on the corresponding function in the definition of differentiability. So for f, we must use function epsilon f. For g, we have another function epsilon g. The only thing we know of these functions is that their limits are 0 as their argument approaches 0. So now we substitute in these two definitions of differentiability for f and g, v equals g of x, v0 equals g at x0, and delta of v equals g at x minus g at x0. So delta of v is given by this last equation. Delta of v is g of x minus g of x0, but delta of v can also be written as g prime at x0 times delta of x plus delta of x epsilon g delta of x. So here we have used the definition of differentiability, the assumptions that f and g are differentiable, and the fact that if a function is differentiable, then it has a derivative, and the derivative is the differential of the corresponding function. We plug the definition of differentiability of the function g into the definition of differentiability of the function f, and we get that f at g of x minus f at g of x0 equals f prime at gx0 times g prime at x0 delta of x plus delta of x epsilon g delta of x, plus the product g prime at x0 delta of x plus delta of x epsilon g delta of x, and that's multiplied by epsilon f evaluated at g of x minus g of x0. This is now rather long and looks complicated, but here we have simply the term delta of v written as g prime at x0 delta of x plus delta of x epsilon g delta of x in the two places indicated by the red underlining. Delta of v also appears as an argument in the function epsilon f, but here we have left it just in the form g of x minus g of x0. Next we expand the first term on the right hand side and we do some rearrangement. When we expand the first term on the right hand side, we get f at g of x minus f at g of x0 equals f prime at g of x0 g prime at x0 delta of x plus f prime at g of x0 delta of x epsilon g at delta of x plus the product g prime at x0 delta of x plus delta of x epsilon g delta of x, and that's multiplied by epsilon f evaluated at g of x minus g of x0. The rearrangement that we perform next is that we first leave the first term intact. So we have that f at g of x minus f at g of x0 equals f prime at g of x0 times g prime at x0 times delta of x. This is the first term in the definition of differentiability for the composed function f composed with g. Then we have the error term, the remaining term, which we have to combine of everything that is left, and we have to show that it is of the form delta of x times some epsilon function that has a desired property. So we first observe that of all the remaining terms, we may take delta of x out as a common factor. When we do that, we get delta of x times f prime at g of x 0 epsilon g at delta of x. This is what we obtained from the first occurrence of this term delta of x after the first term on the right hand side. Then delta of x occurs also in two other places, and from there we get g prime at x0 and epsilon g at delta of x, and that sum has to be multiplied by epsilon f at g of x minus g of x0. So this is now our expression for f g of x minus f at g of x0. So we may next use this presentation for the difference f at g of x minus f at g of x0, and we observe that this difference is now of the form f prime at g of x0 times g prime at x0 times delta of x plus delta of x times a rather complicated long expression. This complicated long expression we called epsilon fg delta of x. And in order to show that the composed function f composed with g is differentiable, we have to understand or see why epsilon f of g of delta of x approaches 0 as delta of x approaches 0. This was the condition we had in the differentiability. So we observe that, first of all, since g was differentiable, the epsilon function for g, epsilon g delta of x approaches 0 as delta of x approaches 0. Also, since f is differentiable, the quantity f, epsilon f at g of x minus g of x 0 approaches 0 as delta of x approaches 0. Because as delta of x approaches 0, x approaches x0, therefore, since g is continuous, also gx approaches gx0. Therefore, the argument of epsilon f approaches 0 as delta of x approaches 0. And by the defining property of the function epsilon f, we know that its limit is 0. So since epsilon fg delta of x approaches 0 as delta of x approaches 0, this proves the chain rule. And in view of the fact that differentiability is the same as having derivative and that the differential is the derivative, this proof is now complete.